So you mentioned financial institutions. Obviously, they have the pockets to be early adopters of technology like this. I've heard a lot of people, even people from the vendor side, say that big data as a phenomenon is still largely vendor driven. Would you agree?
Well, big data is actually the replacement for the buzzword cloud computing. You know, every 2 years we have to change the buzzword that's the buzzword of the next 2 years. And we've just got tired of talking about cloud computing, so we have to change the topic. And this is not new in this business. It happens about every 2 years. You've gone from data warehousing, like you talked about, to software as a service, and then into cloud computing, and now we're into big data. We just can't talk about the same thing all the time. We have to change it.
So that's really just a handle for the conversation.
I really think so. I mean, if you're writing about cloud computing for 5 years, your readers are going to get pretty tired, and they can pretty much know everything you need to know about cloud computing.
You get tired of writing about it.
You get tired of writing about it. So somebody in the industry, and it could be the Gartner type people that say, well, it's time to change the topic to something new. So that's why we're talking about big data now.
Okay. The whole high-performance analytics infrastructure. We have in-memory and in-database and grid computing. How are these complementary to each other? When is one functionally more important than the other?
Well, we refer to grid computing as having a grid manager that knows which machines are busy, so that it can, as new jobs appear, they can be shuttled to the machine that's least busy. Now, what we call in-database, these are taking scoring functions that we've developed offline, overnight, over a time period to develop these models. And once the model is developed, that code is moved inside the database so that you can use an SQL and have a score function that executes that code so that you get back a score inside the database. And with vendors like Teradata, that's all can be done in parallel because they have a shared nothing environment where each process owns a part of the data. Now, we have done all of these things to try to speed up computing, but even then, we were confronted by a user in Singapore that was taking 18 hours to do a risk computation. And when I came back to the US after talking to this person, I learned more about risk, exactly how things were being computed. And then I sat down and tried to estimate how many instructions needed to be executed to do that computation. And it was about 200 trillion.
Good Lord.
So obviously, and this is something that needs to be done. I mean, this involves a lot of simulation, trying to estimate possible market states that could occur, and then pricing all of your items in your portfolio at those different market states. So there is a lot of computation involved, and the basic problem is 3 years ago when we first started working on this problem, processors weren't running but about 2 billion instructions a second. Today they're up to 3 billion. So if we're ever going to make that job run a lot faster, we're going to have to spread it out amongst many processors. And fortunately today with Intel, Intel right now has got the Sandy Bridge chip. And talking about Sandy Bridge, I just happen to have one in my pocket. Don't know if you've ever seen one of these, but that's the size of a Sandy Bridge chip from Intel. It's got 8 cores inside it. Now a core is the CPU, the floating point unit, the I/O unit. It's all inside this, and there are 8 of those. And then you put a little memory up here beside it and put some disk beside it, and you got 8 total computers. The other thing about the Sandy Bridge chip is it's hyper-threaded, so that you can very efficiently run 2 threads on each core. So on this one chip, we can run 16 processes in parallel. And that and each process actually is running at 3 billion instructions a second. So it's quite powerful chip. And this is what is making more and more people have to move to either symmetric multiprocessing, where we take jobs and split them up amongst many of these different processes. Or if the job is really big, we spread it out over multiple machines. So the fact is that this is the way computers of the future are going to be. It's getting almost impossible to continue to make chips faster and faster and faster. Moore's law, everything doubles, speed doubles every year and a half.
But there are like laws of physics that are that.
That's exactly right. This is 22 nanometers, and I can't remember where ultraviolet ends up, but it's 1 or 2 nanometers, I think, maybe somewhere in that range. So we can't go past the ultraviolet, because you get into the X-ray spectrum, which will not etch, just goes right on through. So the future of chips is going to be multiple cores on a chip. So we're up to 8 now with Sandy Bridge, and I expect we'll see 12, 16, perhaps the next go around. So can't make our programs run faster on a single CPU anymore. We're going to have to start spreading out to multiple. And this big data era that we're in now is perfect timing. And the other thing about it is memory has gotten so inexpensive that it's actually, for the big data, we actually put it into memory. So the idea of having to store it huge amounts of data, we can buy a rack of blades that has over 6 terabytes of main memory on it. And that memory we use for about 80% of it we use to put the data in, and we take the other 20% to do the computations in. So in fact, it's a very efficient process.